So without further ado, I am delighted to welcome Dr. Chiara Petrone to the Society. Chiara is the head of volcanopetrology at the Natural History Museum. Her research goal is to make estimates of timescales of volcanic eruptions and thereby improve forecasting of future eruptions and their impact on society. In addition, Chiara also sits on the Geological Society's Council. Chiara Petrone.
Thank you, Elsa, and thank you, everybody. Nice to see you all in person, and thank you to the people online. It's really a pleasure to be here and talk about my favorite subject that happened to be volcanoes. So volcanoes are really important. They are terraforming, terra destroyer. They also impact our everyday life if we don't live close to a volcano, because they produce fertile soil, they produce geothermal energy, and of course, very important, important mineral. But they do erupt, and so they pose the life of people at risk. So the big challenge of volcanology is really to improve our forecasting ability. And in order to do so, we need to answer a few fundamental questions. So when the next eruption will be, how big will it be, and how long it will last? And in the next 40 minutes or so, I will try to show you how we try to answer this question and to progress on this question, but from a slightly different perspective. Look at the petrology side, and so the erupted product. So there are about 800 million people living within 100 kilometers of an active volcano. And most of these volcanoes are in underdeveloped and overpopulated country. Here we are in Antigua, Guatemala, with the towering Volcán de Agua, which is actually an extinct volcano, but is hiding a very active volcano, which is Volcán de Fuego here, which erupted in 2018, claiming the life of 160 people and displacing or forcing the evacuation of 3,000 people. So people that live near an active volcano, they really have a very complex relationship with the volcano, and they really need to learn to manage the hazard from very early on, as we can see from this painting on a school wall in a village close to Volcán de Fuego. And life in this rural area can be quite hard, particularly if the evacuation route is meaning to cross a river, which it can be impossible during the rainy season. I suppose most of us, or all of us, are familiar with a cartoon like this, where we have a volcano with a lot of instruments deployed on the volcano in order to monitoring the volcano and to kind of understand what the volcano is doing on a day-to-day basis, measuring the plume, measuring the seismic activity, the inflation, deflation, the gas, and so on. So for many volcanoes, there are some volcanoes that are really well monitored. Here we are at Stromboli in Italy, and this is all the seismic station deployed on this small island. And these are the gas measuring stations deployed on the island, which are all controlled by the INGV, the Italian National Institution of Volcanology and Geophysics, that look after volcanoes and earthquakes in Italy. And here I am with some colleagues from INGV last year in May, looking for several hours at the volcano with some thermal camera pointed to the crater, so the crater will be somewhere here, and looking at the thermal emission of Stromboli. So it's really important to understand what the volcano is doing on a during the daily activity, but not all volcanoes can be monitored in such an extensive way. And for many volcanoes, we really need to rely on the geological record. And so here it comes the petrology, also because actually the priming of eruption occur in the plumbing system over a medium and long-term time scale. So key information are really located in the erupted product and can be unlocked by by petrology. However, there is a problem with the petrology, or kind of a downside, is that we need the erupted product, we need the rock, so we need an eruption. Therefore, petrology is a posteriori tool, which can be of limited utility for monitoring, volcano monitoring. However, we are getting better, and our analyses are getting faster. And in recent years, what we have seen is the use of the petrology as a near real-time monitoring tool. In this example, some colleagues actually from my NGV, Rosanna Corsaro and Lucia Miraglia, they've looked at the volcanic glass with some rapid analysis of volcanic glass of the product erupted from Mount Etna between December 2020 and April 2021, when there was really a very strong activity of Etna with several lava fountaining, mostly on a daily basis. And looking at the composition of the gas, of the glass, they were able to track the changing composition, so in increasing in calcium, aluminium, which signaled the arrival of more mafic magma from depth. And so they were really able to track how this eruption changed. And the arrival of mafic magma from depth is really important, because it's one of the main processes triggering and priming an eruption. Another example is this one from La Palma, the eruption in 2021. So 2021 was kind of a big year for volcano. Probably you remember there were a lot of volcanic activity. So in this case, Matt Pancras and collaborator, they were kind of sampling the lava flow and taking a small slice of this lava flow, making transparent to light, obtaining a thin section that then they analyze it with an electron microscope, which is able to reconstruct or recognize the mineral phase. So we have the clinopyroxene in green, the olivine in purple, and the plagioclase in blue. And from this, they were actually able to look how the dynamic of the eruption was changing the petrol during the eruption in itself. These analyses were done within 10 days from the collection of the rock, which is kind of quite extraordinary. In their world, basically, in this case, a rapid response from petrology really untangled the complex processes occurring during this eruption. But can we link this data with the petrology data with the monitoring data? So the monitoring data, they really are kind of timing, they are really giving a timeline of an event, almost on an hourly basis or day-to-day basis. But how about the petrology? The petrology tells us that there's new magma arriving in the system. But when? Can we extract this time information? I suppose that you know that the answer is kind of yes, we can. But before showing how we can do this, let's step for 1 minute back and look at the plumbing system of the volcano. Many of us are familiar with a cartoon like this, where there is the so-called magma chamber, a liquid pool of magma underneath the volcano that feed the eruption. And this sort of cartoon served us quite well in terms of understanding the processes. But with new analysis and with more sophistication of analysis, we now know that the volcano plumbing system is way more complex, extend vertically for for quite long distance down in the lower crust. And actually, magma spends most of its life as a solid network of crystal, where the liquid magma is really a limited portion between the crystal. And this solid network is called crystal mash. So all these layers here represent where the crystal mash basically, or where the magma arrive, start for a certain amount of time, crystallize, and then need to be removed and moved up all the way up from the lower crust to the surface, in order to squeeze enough liquid magma and accumulate enough liquid magma to then feed the eruption. And how we can do this? Well, basically, it's the melt that is moving here, remelting what has the magma that's partially crystallized and squeezing the liquid magma and moving the crystal all the way up. So you can understand that actually the crystals are really important, since the magma spent most of its life as a solid network. So let's look at some of the mineral. And here is a lovely chemical map, chemical composition of the pyroxene from Stromboli, where we can see quite a lot of different composition. This is a map, a chromium map taken at the laser ablation. So basically a beam of laser firing to the crystal and making possible to analyze this crystal at very, very fine scale and all the changing composition. So minerals are an archive of information, and I like to call them the volcano messenger because they preserve a lot of information. We can think a mineral growing in layer from the core to the rim in a way similar to the tree ring in a tree trunk. So basically, each of these layers tell us the information about the magma. First of all, the chemical composition of the magma and how it changed while the crystal is growing. So in this case, we can see at least 3 layers, this bright green, which corresponds to a high chromium core, a kind of bluish green mantle where the chromium is lower, and then again a rim where the chromium is higher. So this means that this crystal, while it was growing from the core to the rim, was in contact with at least 3 different magma in different moments of the history of this crystal. So we can extract the chemical information, chemical composition of the magma, the temperature of the magma, how hot was the magma, and also the pressure, at which level in the plumbing system this crystal was growing. But how about the time? Can we extract the time when each of these different layers formed? Yes, and there are 2 ways in which we can extract the time. One is kind of the absolute dating of mineral, which rely on the radioactive element. So it's a radiometric chronometer, which is looking at the decay of any radioactive element, which decay with a sort of at fixed rate. So we can extract an absolute date, and the radiometric chronometer, like the uranium, thorium, or the decay of the argon, they allow to time event in the range from 1 million of years to 100 years. Events, magmatic processes such as the magma differentiation of the storage of silicic magma that tend to be stored in the plumbing system for quite a long time. Then we have another chronometer, which is called elemental diffusion chronometer, which is a relative chronometer. And I will explain you in a minute what this means. And it relies on the diffusion of element across the different boundary of a chemical a chemical zoned crystal. And this diffusion chronometer allow to time event in the range from millennia to hour. Events such as the recharge of the magma, or the gassing, or the magma differentiation. So on time scale that are more relevant with the monitoring data. Okay, so let's see how the diffusion chronometer work. So we have our lovely zoned crystal, a pyroxene. These are images, the backscatter electron images, where the different grayscale are function of the magnesium content, expressed as magnesium number, so the ratio between iron and magnesium. The lower the magnesium, the brighter is the grayscale. So this crystal started to grow in a magma with low magnesium, which also corresponded to higher silica content. And then at some point in time, there was a new magma that formed this dark rim with a higher magnesium and lower silica, so a more mafic magma, a mafic recharge in this case. So if we imagine to analyze the chemical composition across this boundary, in the moment this boundary forms, this chemical boundary forms, we will find something like this, a very sharp core rim boundary. This sharp boundary is in this equilibrium, so elements start to move from one side to the other of the boundary, trying to reach equilibrium. So given some times, this profile will smooth, and the magnitude of relaxation is function of the temperature of the magma. The higher the temperature, the faster the element diffuse, and time. The longer these crystals stay at high temperature, the bigger is the relaxation of this profile. When the eruption occurs, the temperature drops, and elements cannot move any longer across the boundary. So the relaxation of the profile freeze. And when we analyze, we get the erupted rock, and we analyze this crystal, we measure a composition like this from the core to the rim. So, and the smoothing of this profile, we will be function of the time. So we can extract the time, in this case, 10 days. But what this 10 days means? Well, this 10 days means that the 10 days prior to eruption, the more mafic magma arrive in the system and form this rim. So you can see that we can time this event, and this is a relative time, relative to the eruption, the moment of eruption. If we know the moment of the eruption, we can transform this in absolute age. Otherwise, we still have a time information, but it's a relative time information. So which process do we target? Most of the time, we target process like this, the arrival of the mafic magma, forming as last process prior to eruption. And this is a compilation from Costa of several volcanoes, from basaltic volcano in blue and silicic volcano in red, and looking at the time scale of the magma mixing, the last magma mixing event, so the mafic recharge prior to eruption, ranging from 1 day to 1 year. And we can see that the basaltic system, they have a shorter time scale, less than 1 year, whereas the rhyolitic system, the silicic system, have longer time scale. But study like this really refer to the rim. So they look at the rim, and they look at the final process, probably just before the eruption, so triggering the eruption, which usually refer to the shallow level of the plumbing system. If we look at any thin section of any rock, and this is like a chemical map of an entire thin section of a rock from Etna, we will see a lot of crystal. So in this case, the blue sky are the plagioclase, the purple are the pyroxene, and the green are the olivine, and all the rest of the blue is the volcanic glass. If I now extract from this chemical map only the purple one, only the cyanopyroxene, I will have something like this, which is a bit crazy. But you can see there are a lot of crystal with different size. So this means that this rock, every single erupted rock, contain really a large variety of crystal, grow in different moments, so some are bigger and some are smaller, and they also are very complex. They show a very complex zonation, and we can see the zonation here from the different color. And so this tells us that in each rock we have this rich, large variety of crystal that they kind of record different process or different moment of the same process. So for a simple crystal, simple zoned crystal like this, if we look at only the rim, is fine because there is only one event. But for complex zoned crystal like this one, if we only target the rim, it's like trying to infer the life of a tree just from the last ring. which is probably not ideal. But now we can actually extract the time information from multiple compositional boundary, trying to deduce the life or the timing multiple event across the life of the crystal, doing what I like to call elemental diffusion chronostratigraphy. So really look at the stratigraphy of this crystal in terms of the time scale of event. So how we can use this tool that allow us to extract time scale in order to understand the volcanic plumbing system and trying to get better at forecasting eruption. I will show you 3 examples. The first one is from Popocatépetl volcano in Mexico, or Popo for short and for friends. And in this case, it's more like a forensic volcanology approach, looking at the past activity. Because as I told you at the beginning, not all volcano can be very, have a monitoring network, a well-developed monitoring network. So in many cases, we really need to look at the past activity, well, or in all cases, actually, it's better to look at the past activity because we learn from the past, as we know as geologists. So here we are in Mexico. This is towering Popocatépetl. It's 5,500 meters tall in height. There are about, it's not far from Mexico City. It's about 70 kilometers from Mexico City. There are about 23 million people living in the shadow of Popo. So quite a lot of people. And the past activity of Popo looks something like this. This is a stratigraphic column from the last 23,000 years of activity. There have been several periods of effusive activity, all these different color, layer of different color, but there have been also quite a lot of big Plinian explosive eruption, like the Xochimilco eruption, 23,000 years old, the big Plinian eruption, the Pumice andesite, 14,000 years old, and then another one, 2,000 years old, and the most recent one, the pink pumice here. If we look at the distribution of this material, the Plinian cloud during this eruption really depends on the wind, particularly the time of the year, but in some case, it can reach Mexico City. This is the 14,000-year-old eruption. In other case, it goes south, and in other case, will go north. So really depending on which time of the year and where the wind is blowing, there are the area at risk is really, really large. What Popo is doing now? Well, since 1994, when the activity restarted, the activity is characterized by, it's mostly up in the crater, so not too bad. And it's characterized by this activity of dome forming and dome destroyal. So from time to time, after the dome is formed, Popo clears its throat and destroys the dome with some more energetic explosion that can reach the village and town nearby. The thing that we don't know is if this activity will kind of lead to a Plinian eruption, or we stay in this way for how long. So in order to try to answer this question with Martin Mangler, a former PhD student of mine, we have been looking at several eruptions. 2 big Plinian eruptions, the 14,000-year-old, the 2,000-year-old, characterized by a VI6. What is VI? It's volcanic explosive index, which on a scale between 0 and 8 tell us how explosive is this eruption. This is 6, so it's quite explosive. Then we have looked at some less energetic Plinian eruption, but still quite big, the 23,000-year-old and 1,000-year-old, and then 3 effusive eruption intercalated with this Plinian eruption. These blobs are all period of mafic recharge. So how long each period of mafic recharge lasted with the time scale extracted from the mineral. And here is the timeline. So 500 year up to 7 days, okay? So if we look at this, first at the big Plinian eruption, we can see that in order to have some big Plinian eruption, we have like a long recharge period with several periods of mafic recharge. And this long period of recharge starts about 200 years prior to eruption. And is followed by a period of around 1 year of stasis, of hiatus, where the volcano is not doing anything. It's basically building up the eruption, degassing, building up the gas, and then exploding. So good. Seems like quite a good news. Particularly if we compare this with the pattern of recharge for diffusive eruption, where we have less period of few period of mafic recharge, starting about 10 years before the eruption and lasting until few days before the eruption. So we have a very good way to discriminate these two, the big Plinian eruption and the diffusive eruption, which is a great news. But if we look at the less energetic Plinian eruption, the news are not so great, because we still have a lot of mafic recharge period, starting a little bit kind of 20, 30 years before eruption, but lasting up to the few days before the eruption, a fashion more similar to the diffusive eruption. And this poses a big problem when we're trying to interpret the current activity of Popo. So more studies are needed in this case. Okay, so, but how about correlating the time scale with the monitoring data? Can we actually use the Petrology in this case as a monitoring tool? But let's see another example and remain in Mexico. We just move a little bit west here, Colima volcano, another big explosive volcano. Again, characterized by, this is the crater of Colima, characterized by the dome building activity and dome destruction. And during the explosive activity, when the dome is destroyed, this is mostly associated with pyroclastic density current, so avalanche of hot material, which kind of move down the flank of the volcano. We have been looking at this eruptive period from 2013 to 2017, which we divided in 6 periods. And this period is characterized by major explosion that destroyed the dome and associated pyroclastic density current, some period of dome growth, and some period of lava flows. Interesting, there is this phase 3, which is characterized by the Plinian eruption, the biggest one in the last century at Colima, which occurred in July 2017. Okay, so let's look at the crystal, and in particular to the pyroxene. I suppose now you understand that pyroxene is my favorite mineral. And particularly the reversely zoned pyroxene, where we have a core which is characterized by low magnesium, and then is surrounded by a rim characterized by high magnesium, so the mafic recharge that arrived prior to eruption. But how long before the eruption? Well, here we are, all the data. Each of these points is a time scale from a crystal for the different period. And here is the timeline of event. Mafic recharge starts about between 2 and 1 year before the eruption. They last up to few days before the eruption, depending on the crystal, because I remind you that we have a lot of crystal, a variety of crystal that record different processes at different time. Okay, so since we know when these rock were erupted, because the period is very recent, so we know when they were erupted, we can transform this relative time scale in a timeline of events. And here we are from 2013 to 2016 for 3 of these eruptive phases. These are the single point of mafic recharge, so the single time scale transformed in this way, basically, where we have kind of a more time scale, we have a peak here, okay? So, and depending on the frequency of eruption and how the time scale cluster, we were able to deduce and to infer several periods of mafic recharge, highlighted here in this with this black arrow. And in some cases, we have only one mafic event of mafic recharge. In other case, we have multiple events of mafic recharge, followed by a last mafic recharge, which is actually the triggering of the eruption. And we can see that some of these mafic recharge, they overlap between period, which means that some of the crystal that saw this mafic recharge, then they were not erupted, they stayed in the system, in the magma chamber, in the reservoir longer, and they were erupted with the following eruption. Okay, so if we look here, we have all the timeline of this mafic recharge event from the Petrology from 2013 to 2017. And we infer 3 big periods of mixing, 1, 2, and 3. And I apologize for this very busy slide, but all these are the monitoring data. So here we have the rock fall, the explosion, the seismic data, the tremor duration, and here the gas flux. And when we compare the timeline of the Petrology event, so our arrival of magma recharge with the monitoring data, we can see some interesting things. In period where we have a low frequency of mafic recharge, as in this period 1, actually there is no correlation with the monitoring data, probably because the magma is not enough. It's not making really any impact on the surface. But more interesting, in period where we have a higher frequency of mafic recharge, like mixing period 2 and mixing period 3, then we have a very good correspondence with the monitoring data. So the mafic recharge are more frequent, and we have a very nice peak of increasing in the gas flux, increasing in tremor, increasing in the seismic activity, and so on. So what this means in terms of the volcanic plumbing systems, it means that we have a mafic recharge, so magma that arrives at shallow level and stops here because we don't have the eruption yet. This is just the first mafic recharge event. But at this point, the volatile, they separate from magma, and here we have the peak of gas, and they start to ascend, and at the same time, they cause seismicity, and we start to see the seismicity. Then the process repeat, another magma, another recharge arrive, volatile, they separate, they start to they cause seismicity, and we have all this peak. Finally, we have the last mafic recharge event that triggered the eruption, because the system is now primed for eruption. So we have really a good way to correlate the petrology data and the monitoring data, and this is really useful for interpreting future monitoring data. But does this system works for other systems? Well, let's look at Stromboli, volcano in Italy. Okay, so Stromboli is well known for the Strombolian activity, characterized by a small explosion here in the crater every 20 minutes or so. But in the activity of Stromboli, there are also some more energetic explosive activity that we divide in major explosions, which are just slightly bigger Strombolian, and paroxysm, which are very energetic explosions that last very few minutes, and they produce a very high plume, several kilometers up into the atmosphere. They can also be associated with some pyroclastic density current that rain down this very unstable flank of Stromboli called a Sciara del Fuoco, and they can cause tsunami. What we know about the Stromboli plumbing system? Well, we know that the normal Stromboli activity and many of the major explosions are fed by this blue magma, which is a degassed crystal-rich or high porphyritic magma, HP magma, that is situated here at shallow level, between 2 and 3 kilometers. There is also another magma, which is a volatile rich, low porphyritic magma, LP magma here in red, which is situated between 7 and 10 kilometers. This volatile rich magma, the LP magma, is erupted only during the paroxysm alongside the blue magma, the high porphyritic one. But the continuous refilling or the continuous arrival of this volatile rich magma in the shallow reservoir is what is kind of controlling the activity of Stromboli. But we only see this occasionally. Paroxysms are big event, but they are rare event occurring every few years. There was one in 2003, one in 2007. But in 2019, there was a very unusual sequence of events with one major explosion on 25th of June and 3 paroxysms, one on the 3rd July and the other one on 20th of August, occurring within 64 days. And this is the plume of the 3 July paroxysm. So, of course, I wanted to know what was caused this unusual sequence of events. And I look at my dear paroxysm. Here is all the variety of paroxysm that are found in these 2019 rocks. In terms of composition, they are quite similar to all the paroxysm erupted during the present day activity. And there are 2 big compositional type. One is characterized by this low magnesium. This is the value of the magnesium number. So low magnesium, light gray portion, which is an augitic composition. And the augitic composition, the low magnesium one, they are in equilibrium with the shallow magma, the blue one. So they grow in the shallow reservoir. And then there is this other composition, the dark gray one, which has high magnesium, so it's the more mafic magma, and is in equilibrium, the diopsidic in composition is in equilibrium with the gas-rich, deeper magma. So let's look at this paroxysm a little bit better. Here are the backscatter images. So the light gray, the low magnesium, and the dark gray, the high magnesium, compared with the compositional map of some trace element, chromium and nickel. And why chromium and nickel are important? Because chromium and nickel, they go hand in hand with magnesium. So if there is high chromium, high nickel, there is also a magnesium, which really tell us when the mafic recharge or the mafic magma arrive. So what we can see here, we see a variety of texture. For this crystal that have like, in some case, like we have crystal that are characterized by a low magnesium core, which can be surrounded by, again, a slightly higher in magnesium, but still low magnesium rim, like in this one, or in other case can be surrounded by a very dark rim, which is the high magnesium one, which is also characterized by high chromium and high nickel. So this dark rim, this diopsidic rim, they really tell us when the mafic recharge arrives as the last event prior to eruption. And then there is this other group of crystals which are characterized by diopsidic composition in the core. And these crystals, they are the crystals that form in the deeper reservoir in equilibrium with the red magma, the volatile rich magma. But we can see quite interesting this core here, which is a high magnesium core, but it's very unhappy, and because it's been kind of remobilized by the deeper portion and brought by the deeper magma up in the shallow reservoir where it formed this low magnesium rim. So we have the evidence of the arrival of the mafic magma here, the evidence of crystal that formed in the deeper reservoir, and then we have crystal that just formed in the shallow reservoir, like this one. But this crystal and this other crystal, they have a very, very crazy rim characterized by a strongly zoned chromium, but not strongly zoned nickel and very low magnesium. So this means that actually this strongly zoned chromium is not due to the arrival of mafic magma, but it's due to the fact that they formed in the shallow reservoir, but this shallow reservoir was not in a quiet status, but was in a very convective and chaotic mixing regime. Okay, so now if we look at the time scale of this event, so when the mafic magma arrived and formed this rim, or when this crazy rim formed, or when this crystal was erupted, what this tell us? Let's look one by one this crystal. This is a timeline, a relative timeline, which tell us the time of injection in days from 1 day to 1,000 days. For the three events, the 25th of June major eruption and the two paroxysms, 3 July and 28th of August. Let's start with this crystal, the crystal that started their life. So they started to crystallize in the shallow reservoir because they have a low magnesium core. And then the mafic recharge arrived in the shallow reservoir, forming this rim. And the mafic recharge arrived in the shallow reservoir starting about 30 days, so 1 month prior to eruption, up to the eruption itself. So actually it was really the arrival of this deeper magma triggering the two paroxysms. And this, the big role played by the deeper reservoir in triggering the paroxysm is also confirmed by the crystal, that the high magnesium crystal that formed in the deeper reservoir, which have time scale here, the triangle 1, which completely overlap with this, the triggering of the eruption. So this means that the mafic magma started to rise quite rapidly, carrying some of these deeper crystal, okay, which had no time to react in the shallow reservoir. But how about the last type of crystal? This one with the started to grow, they form completely in the shallow reservoir, kind of initially in a quiet environment and then in a very chaotic environment. What caused this chaotic environment? So here we have the time scale, all in green. So the chaotic environment started about 400 or 500 days before the eruption, but really the time scale overlapped completely with the arrival of the mafic recharge. So this means that when the magma arrived in the shallow system, really enhanced this chaotic regime. So the arrival of the mafic recharge of the deeper magma really perturbed the shallow system. Okay, we can transform these now in a absolute timeline of event from November, December 2019 to the 28th of August. And this is the timeline for the Petrology data. We can see that the mafic recharge started sometimes in end of 2019, but then really consistently in a very consistent way started a month before eruption, leading to the first paroxysm. And then a second mafic recharge led to the second paroxysm. If we now compare this with the monitoring data for the same period, the gas signal, the increase of gas from a work of IUPAC, and then the hour explosivity from the work of Andronico, we can see actually a very good correspondence. The mafic recharge arrive and all these signal really increase. So this means that two things. Well, that in this case, the gas and magma remained coupled, not like Colima, where the gas the system started to degas prior the eruption. So they remained coupled all the time until the driving the eruption. And also, more importantly, probably, it means that the petrology data and the monitoring data, they really talk to each other. So it's really useful as a monitoring tool. Okay, so what this means in terms of the plumbing system of Stromboli? Well, this is a cartoon that show what we think was the situation between June and August 2018 for the plumbing system of Stromboli, where we have a mafic recharge that arrived quite rapidly in the shallow system, mix rapidly, and then erupt. And it seems that the mafic recharge can arrive almost without no obstacle. And this situation is very different from what we found from a previous study for a previous period, the 2003-2017 period, where the mafic recharge had to make its way through a very clogged plumbing system. And all this gray stuff that is clogging the plumbing system is the crystal mash. And we have a lot of evidence of remobilization of the crystal mash in this period. We don't have evidence of remobilization of the crystal mash in this period. So this means that between 2003 and 2017, the magma arriving from depth was really able to remobilize the crystal mash, destroying the crystal mash almost completely, leaving a very direct link between the two reservoirs, the deeper and the shallow reservoir. And this rejuvenation of the plumbing system really determined a more energetic activity or more variable activity with almost an immediate response from the arrival of the deeper magma to the surface. And actually, last year, in July, 11 July 2024, there was another paroxysm at Stromboli. Okay, so this is all that I have to say. Thank you very much.
Thank you so much, Chiara. So just a reminder, if you have a question in person, raise your hand and Samira will run around with the microphone so those online can hear you. And then if you're virtually joining us, you can post your question in the Q&A function on Zoom and we will read it out. Anyone in person got a question? No? Oh, yep.
Thank you very much for the talk. Very interesting. The last slide, you've managed to graphically show what's underneath the ground.
This one.
Yeah. How'd you do that?
Well, a bit of imagination, I suppose. Quite a lot of imagination. Well, so there are things that we know. So from melt inclusion, we know we know where the shallow reservoir is. Also from melt inclusion, we know where the deeper reservoir is. We know that the crystal mash is present because we have evidence, and the evidence are mostly, you remember the high magnesium core that was really unhappy? Those are portion of the crystal mash. And it's not just that I'm saying this, is because we have like the isotopes composition, apart from the composition that there is more mafic, so they cannot be formed in the shallow reservoir because they are in equilibrium with the deeper one. There is also the isotopic composition that allows, that is kind of similar to something that at some rock they were kind of older than the previous the present day activity, and also the fact that it's so unhappy, so resorbed, means that actually there was an hotter magma that's remelted that crystal before bringing that crystal into the shallow reservoir. And the only way is that those crystals were somewhere here. We don't know exactly where. But then the deeper magma arrived, is remobilized, kind of remobilized, that destroyed the portion of the crystal mash and brought the crystal here in the shallow reservoir, living there for a while until it was erupted. And actually, one thing that I didn't show you is the time scale of that crystal. For the 2019, the time scale for those core tell me that they were remobilized mid-2017 mid-2017. So they were remobilized by previous mafic recharge unrelated with the triggering of the 2019 paroxysm. So they were remobilized probably during this period, but they were not erupted. They stayed there for longer until they were erupted in 2019.
Great.
So there is a bit of imagination there. I mean, we don't know if it's this way or, but yes.
Thank you so much. So we have a question from Tara, who's joining us online. Tara asks, how would you identify minerals where the growth has been influenced by crustal assimilation, and how would they differ from minerals with zoning affected by different magma mixing events?
Oh, that's okay. So, well, one of the things will be if there is crystal assimilation. Well, first of all, I mean, it's the texture. So we still have zoned crystal and some disequilibrium, so some anepic crystal. Okay. If it's crystal assimilation, we expect that the magma, the liquid that's produced, that's a portion of the crystal, will have a very different composition from the magma in the system. And so from the chemical composition, also the isotopes, I mean, the isotopes, if we're going to analyze the isotopes, that is really what will tell us for sure if it's crustal assimilation or not, because sometimes if you can have crustal assimilation, but with something that is kind of similar in composition, but usually the isotopes will be different. So a combination of factor, textural and chemical.
Great, thank you.
How and when do you collect your samples?
How and when I collect my sample? I do field work quite a lot. So depending, I mean, for this one, for the 2019, since the eruption, they were so unexpected, literally, they were sent to me from my colleague from ANGV. Same for the paroxysm of 2024, but in other case, I mean, all the Colima sample, all the other Stromboli sample, Etna sample, I go there and I collect.
So you're confident they come from that particular eruption?
Oh, the 2019, yes. Yes, I'm. For the 2019, I'm totally confident because actually they destroyed some of the monitoring station. So we have the exact time where they were erupted and destroyed the monitoring station. And they were collected few days after. Same for the 2024, same for all the Etna sample. My colleague in Catania, they spend really long time as soon as there is an eruption, going and collecting ash literally as it erupts. So yes, for other sample, no, I'm less confident, but for this one, yes.
Great. We have another question online from Steve. Steve asks, how specific is the data to each individual volcano, and can it be used generically as a possible predictor?
Well, each volcano is unique as the unique eruptive history and unique way of changing eruptive style. However, some of the processes are the same. I mean, you hear me talking about mafic recharge for all the talk, because it's one of the main processes that drives the eruption. Magma mixing, differentiation. So the processes are the same. So we cannot apply exactly the time scale, but the principle, yes. I hope this answered the question.
Very good talk, very interesting. Amazing that you can sort of infer so much about what's going on under the earth by looking at individual crystals. quite amazing. I have a question about the step function in the composition.
Yes.
Potentially you could go back to that slide
Yes,
if you
okay.
could.
Just give me 1 second. Trying to do very, very
It's
quickly.
probably quite early, isn't it?
Almost there.
Yeah.
Uh,
I have two questions about this really. Like, first of all, is how do you actually physically, what are you doing at the computer to get this? Are you drawing a line sort of manually on each crystal? Is that how you
Okay,
draw
so
your?
in this particular case, since I'm using the grayscale value as a proxy for the chemical composition, so I draw a line here at the electron microprobe, and I analyze the profile, okay, so along here.
You're choosing those manually, sort of.
Well, I mean, the electron microprobe is basically firing a beam of electron through the crystal, and you have this the software allow you to say, I want a line there. Okay, so I draw a line perpendicular to the boundary here, and I get the chemical composition, which I need to extract the temperature and to know how the change in composition. But then actually the physical process of diffusion, I do using the grayscale as a proxy, because the resolution of the electron microprobe, even if I go to 3 micron, is not enough to have a really good slope here. Okay, so there is a I've published a MATLAB code in this particular case, which allow you to extract the gray value along a rectangular shape. So you just draw a rectangular shape and extract the gray value, basically 100 lines, one close to each other. And then you get an average, which are all these points, okay? And then there is another MATLAB code which is published that I use to fit the curve, knowing the temperature. So you have to input the temperature, the diffusion coefficient, and in the diffusion equation, and then you get this with the error.
Yeah, excellent. It sort of brings me to the second question, which was how do you differentiate between the temperature and the time? But you know the temperature from the composition directly.
You get the temperature from other evidence, for example, for mineral liquid equilibrium. So you really need to know at which temperature you are looking at the.
I see. You get that from a different source, sort of.
You get from a different
All right.
source, and you can also apply 2 different temperature, because if the system is changing in temperature, you can actually apply the 2 temperature as well, particularly when you look at multiple events.
Great. We have time for one more question. Well, 2 in 1. So we have a question, generally speaking. Could you suggest any particular courses in geology for prospective undergrad students in the UK? And also, what advice would you give to an A-level geology student who wants to pursue a career in geology?
Okay, so well, by any means, do geology. It's fantastic. There is a lot of it's fascinating. I mean, you get into the field, you get to understand a lot of things, how this planet works. In terms of course in geology, well, there are a lot in UK, depending where you are based. It's there's Imperial, UCL in London, but also Bristol, Leeds, Liverpool, lots of places depending on that do very good geology and very good petrology, I would say. Oh, well, clearly Cambridge, Oxford, I mean, I'm not even naming them.
Thank you so much, Chiara. I believe that's all the questions we have time for. So just a quick round of applause.
Thank you.
So the drinks reception will take place in the lower library. And just to remind you all, We've been very good at planning this year, our public lectures. Our next public lecture will be on the 20th of May with Professor Ian Stewart, and it will be Restorifying the Planet Earth, Narratives and Storylines for Publics and Policy Makers. Thank you so much for coming.